All right, hi everyone. We'll get started. So welcome back to another week. Sorry I was not here last week for a review session. In the future, before exams, I will have a longer review session for y'all to ask more questions. Apologize for the timing of last week. And then additionally, if you do the practice problems each week, I'm catching up on those. So you'll have like 3 weeks of practice problems to do by the end of this weekend. So just as a heads up there. Um, any questions for me on the class before we get started? No? Okay. Anything we want to see today? Questions we have? Could be anything and everything.
I think this was gonna be on the quiz.
For Monday? Yep. Okay, let me pull up the slides. All right. All right, so today we started talking about the electromagnetic spectrum. So when we talk about right, what we're talking about here are waves. Everything that can be defined on the electromagnetic spectrum always has a wavelength and a frequency. Right? It will always have a wavelength and a frequency and an energy. So if we look at a wave, right? If we look at a wave, the wavelength is going to be the point from a node to a peak to a trough and then back to a node. So we have one wavelength from red dot to red dot, and then we have another wavelength from red dot to purple dot. They're uniform, usually. I'm drawing. Okay, so this is your wavelength. That's represented by lambda as your wavelength as well. How is wavelength related to frequency?
Inversely.
Inversely, right? So wavelength and frequency are inversely related. So the longer the wavelength, what does that mean about your frequency? For a long wavelength, you have low frequency, right? So long wavelength equals low frequency. It was an example of a long wavelength. Like on the electromagnetic spectrum, which one would be an example? Red light, yep. So you can do red light is a long wavelength in comparison to like what? Green, right? Green, blue, purple, those are all shorter wavelengths. Does anyone know what the longest wavelength is? So your radio waves, those are going to have the longest wavelengths and the shortest or the lowest frequency. Okay. So relative in terms of like when you're comparing stuff, so red light to purple light has a longer wavelength than a lower frequency, but radio waves to red light, radio waves have the longer wavelength and then the lower frequency. So right, so then that means that short wavelength equals high frequency. Right, and so something that is has a short wavelength, right, in comparison to red dot, and this one has a much shorter wavelength. So in that certain amount of line period that we have, assuming that those are the same, right, we have much more frequent occurrences of that wavelength at a time, right? So that's what that means in terms of inverse of long and short wavelengths.
Question.
Yep.
Is your wavelength exactly the same length as your amplitude?
So your amplitude, this is your amplitude.
Would it be, yeah, like, is your wavelength?
This is your wavelength.
Oh, okay. Not, okay.
Right, does that make sense?
Yes.
Yep. So I guess it's the lengths of like two
Yes,
amplitudes. Yeah. A peak and a trough. Okay. And then how do we relate frequency to wavelength?
Equation wise?
Mhm.
It would be,
What connects them?
find it.
Multiply them, and what did they equal when you multiply them?
It'd be
Your constant. What does anyone know what that constant is?
3 times 10 to the negative 9.
Close. So we relate frequency and wavelength to the speed of light, which is your constant c. Frequency is at f, or it's a weird v. Either one of those you might see interchangeably. I use the fancy f for frequency because I think that's makes more sense. So either one, right? It's on your formula sheet. I believe your formula sheet gives you the fancy v for frequency. Right, but we relate wavelength and frequency to the speed of light, and the speed of light is 3.0 times 10 to the 8th meters per second. Okay, so if you know the wavelength, you can always find the frequency because you could just relate it to the speed of light. The speed of light might be given to you as like 2.998 on your formula sheet. Use that one. 3 will get you the correct answer every time. But on an exam or on a quiz, use the number that's given to you on your reference sheet. Okay. All right, the other thing that we can talk about with waves is the energy associated with it. So how is energy related to this? If we have a high frequency, what does that mean about our energy? Our energy is also high, right? So energy and frequency, what is that relationship called? Perfect. Are directly related. So high frequency means high energy. Does anyone know what our highest energy wavelength is, or type of wave is? So gamma ray is highest energy. I suggest that you kind of memorize the electromagnetic spectrum. I don't think that's going to be given to you on your exam or on your quiz. And I think Dr. Bengali wanted them to know that last year. So I would recommend doing that this year as well. Do you want to go over what the electromagnetic spectrum looks like? Yeah. This spectrum that we're, yeah. There are some tips and tricks to figure it out, so it shouldn't be too hard to memorize. But you still got to know it. So I always write my spectrum from low energy to high energy, left to right. So if you have low energy over here, you'll have high energy over here. And then I always put my visible spectrum in the center, because that's kind of my starting point. So if I have my visible spectrum, if I have, right, and that's Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. If I'm looking at low energy and high energy, where does red go? It's left or right? What has a higher frequency, red or violet light?
Oh. Violet?
Violet light has a higher frequency, which means the lower energy is the red light. Yep. So red is going to go on this side. Violet will go on this side. Right? And your colors can fit in between there. Then you have, right on the outsides of your visible light, you have your infrared and ultraviolet rays. Right? Infrared bleeds into red. So infrared is going to go next to red, right? Because it's red to red. And then ultraviolet will bleed into violet because, right, you take violet and you make it ultra. You're getting higher energy. So you have to go closer to the higher energy side. Okay, I then fill in my outsides. I always remember what is my lowest and highest energy waves. Your lowest, we said, was your radio waves. And we highest, we said, was our gamma rays. And does anyone know what goes in between those last two boxes or the last two lines?
Microwave and X-ray?
Microwave and X-rays. So which one, where is microwave gonna go? Microwave will go on the left. And your X-rays will go on the right. All right, and if you think about it, you can see purple. You can't see ultraviolet rays, and that comes from the sun. And those don't like penetrate your skin, right? You can't take an X-ray with an ultraviolet ray. So your X-rays, right, if you need to go to the doctor, that has to be more powerful than something that can tan you. And then gamma rays, I know, are my highest energy. Then for infrared rays, right, that's right next to red. And I know that a microwave can heat my food up, but if I put my food in front of a radio, it's not going to get any hotter. so that I know my microwaves have to have a little bit higher energy than my radio because that needs to put some heat into my system. So I know that that is what's going to go in between them. Okay, so you can kind of conceptually think about what's going on with your waves to try and figure out the electromagnetic spectrum if you forget in a pinch. But I like to build it up this way where I know I have my visible light in the center with red and violet. I then have to flank it with the infrared and the ultraviolet next to the colors so that it has in its name as well. I know my extremes, and then I just have to fill in my middle ones. Okay. So I would just kind of try and find some tricks for yourself to memorize that, but I do recommend memorizing the electromagnetic spectrum. Excuse me, I'm dying. Okay. And then if you remember low energy and high energy, then you can also remember which ones are low frequency and high frequency, because if you remember the trends, then you can fill it in that way. And you only need to remember like one side. So if you remember just the high energy, you know that that is also high frequency and therefore low wavelength. Then you know that the opposite side of the spectrum has to be the opposite of what you just memorized. So if it's high energy on the right, it has to be low energy on the left. If it's high frequency on the right, that means it has to be low frequency on the left. And if it's low or short wavelength on the right, that means that it has to be long wavelength on the left. Right? So if you just remember high energy stuff, then you know what's going on with the low energy. Hey, any questions there? Okay. So then the other thing that we can talk about is just right, energy is related to a constant times frequency. So again, this shows you that H is a constant. It's Planck's constant that will be given to you. It's 6.626 times 10 to the negative 34, I think, if I remember correctly. And then, right, your frequency is just in frequency. And that's in hertz or 1/seconds. So then, and this is in joules times seconds. So then if we know that energy is related to a constant times frequency, and we know that the speed of light is related to the wavelength times frequency, then we can solve this equation for the speed of light over wavelength, and then we know that energy is equal to hc over lambda. So you don't even need to solve for the frequency sometimes if you know the wavelength or the energy. You can just use your constants to find one or the other. I don't think this last equation is given to you on your formula sheet. It might be if he's nice. But you can always solve for it given the other two. Hey, do you want to practice with that last equation for a question?
That's up there right now, you don't think will be given to us?
I don't think that's given to you.
Okay,
Right, but you're given,
would we be given all, like, enough information to make that equation?
yes, you would be given this equation, this E is equal to lambda frequency, or sorry, E is equal to H times frequency, and you're given C is equal to lambda times frequency. So you can solve for frequency and plug it into the other one.
Okay.
Yep.
Never solved with nanometers, like in any of this, we can't, like, I know, like, when we were doing most stuff, you could use liters, and then sometimes you use like milliliters, and it would just work out.
Yep.
Is this the same case, or no, never?
No, this one I would usually convert to meters for all of them.
Okay.
Excuse me. So I recommend like knowing what nanometers are. That's a pretty common unit during this unit.
Okay.
So does anyone know what it means to be nano? Like what that exponent is? So, yep, 1 meter is equal to 1 times 10 to the 9th meters. So if you have 795 nanometers, do you have a lot of meters or a little meters? You have a little. So this means 795 times 10 to the negative 9th meters. All right, so anytime you see N, I just put in times 10 to the negative 9. I don't even change, like, I just put 795 times 10 to the negative 9. You don't need to do proper scientific notation.
Okay.
Yeah. So if you were to solve this, and then do notice that your units all cancel out. All right, you have seconds that cancel out, and then your meters cancel out. So you're just left with joules, right? Energy is an energy unit, and joules is an energy unit. So for energy, I got 2.5. Doesn't look like a 2. 2.5 times 10 to the negative 19 joules. Do note here that a lot of your answers when it comes to this unit, energy is going to have an exponent of negative 19. A lot of the time, that's going to be the case. So if you're doing a problem and you get like an energy unit of 10 to the 19th instead of negative 19th, that should be a red flag for you to just kind of check and make sure you did all of your exponents correctly. If it's, negative 18, negative 20, negative 17, you can still probably trust your answer. Maybe just plug everything in one more time. But negative 19 is a very, very common exponent for energy. Nanometers for your wavelength is very common here. So if you're not getting nanometers, right, that should also kind of be a red flag. Most things will be in nanometers here in terms of wavelength. Frequency, your frequencies will be a lot of 10 to the 14th. So just pay attention to that too if you're getting frequencies of that nature, of that magnitude. Just as a heads up. Okay, any questions with that? Okay.
Let's see, always getting hurt.
Usually it hurts, yep, which is just 1/seconds.
Okay.
Yep. And so you can see, like, for your energy is equal to H frequency, your H constant is in joules times seconds, and then frequency is in 1/seconds. So those will cancel out to give you an energy unit of joules. Okay, I think that's the big stuff from class today. I think you got a little bit farther, but in terms of not overwhelming you on the same day, I think that's a good place. How are we feeling about ideal gases and gas laws and stuff? Do you want to do a little bit of practice with that?
Do we have a quiz?
I think it should be. I think you talked a little bit about like combined gas law for your last quiz, but I don't know if you had ideal gas law on your last quiz. I don't think you did. I can check that. Yeah. Yeah, I think you should have ideal gas law on this next one. Is that something we want to review?
Yeah.
Yeah, okay.
What quiz is Monday? Is it?
Monday.
Okay.
Yep. I'll look at the calendar right now, just so I'm not lying to you. No, you will have a quiz the week of March 3rd. So you have 2 weeks.
Okay.
Yep. But you'll probably have some form of gas law question
Okay.
on the quiz. Yep. So for your ideal gas law, does anyone know what that is?
PV.
Good. Yep. So PV is equal to nRT. All right, this is your pressure. This is your volume. This is your moles. R is your gas law constant. Does anyone know what R value we use for ideal gas law? Mhm. And then T is temperature. Okay. This is for one state condition of your gas to remember, right? If you're gonna change your states, then R stays the same. So then P1V1 over N1T1 is equal to P2V2 over N2T2. Okay, so this is for like a specific instant. And then this is for changing conditions. I think since you were quit or examined on this, tested on this, it might only be one question on your quiz. So I wouldn't worry too much about the ideal gas law, but don't forget it. It will come back later on in the semester. So just your breakdown of that real quick. How far did y'all get in class today? Do you know what slide you got to? Right, you didn't start talking about emission and absorption.
You ever like flame analysis? Basically, it's right after lung vector. Basically,
Okay, so you started talking a little bit about emission and absorption. Okay.
yes, we got to that.
Okay. Okay. So let's do a couple problems with energy and stuff. Right, because we also talked about, right, he talks about binding energy. In the photoelectric effect, just know that that's one energy. You don't really ever need to solve for both of them. You just need to know that the energy has to be greater than, right, the energy in order to emit it or absorb it, whatever that is. So that's my thing there. Don't be confused by that formula in your slides. Okay. So let's do. So I guess before we do questions, one more thing to talk about is absorption and emission. If we're absorbing, what are we doing to our atom? Or what are we doing to that particle? Are we increasing its energy or decreasing its energy? We're increasing energy. Yep. And we're usually increasing the energy of the electron and therefore the atom. And for emission, what are we doing? We're decreasing or releasing energy. And this is in the form of a photon. Okay, so if we look at an atom, we have our nucleus in the center. Right, and we have certain energy levels associated with it. We can have an electron that's close to the nucleus. And if we absorb energy, this electron jumps up to a higher energy level and now hangs out here. This is absorption. Anywhere on that n=3 circle is all the same energy, right? Energy is quantized, and so it remains that same for a certain distance away from the nucleus. Right, so the energy at n=1 might be 100, at n=2 might be 500, and at n=3 might be 2000. Right, so energy has to be gained in order to go from n=1 to n=3. right? If I had 1,000 joules worth of energy, what N level would I be at? If I only had 1,000, where would I be?
Then, yeah, 1,000.
If I had 1,000, why would I be at N2? Yep. So my energy is between N2 and N3. But in order to be at N3, I have to have 2,000. I can have any sort of energy from 500 to 1,999. But until I have 2,000 energies worth of energy, right, I will not be able to make it to energy level 3. I have to stay at my 500 level until I have enough energy to jump to that next one. Right, so you have to put enough energy in order to increase the energy of that electron. Does that make sense? Right, so then in order for me to go from n equals 3 to n is equal to 1, right, if I go down n equals 3 to n equals 1, oops, right, I've now lost 1,900 joules of energy, we'll call it, right? So this is emitting or emission if we go from a higher energy level to a low energy level. Right, to go from n is equal to 3 to n is equal to 1. And where does that energy go? It goes into a photon, right? So that change in energy, that energy that I lost when I went from n equals to 3 to n equals 1, is now the energy that's related to h times frequency, or hc over lambda, right? There's now a frequency and wavelength associated with that photon that was released when I dropped down in energy. Right? Think about after you did something high intensity, right? You're all tired and you like slump over and you release a sigh, right? And you bend over. That's the same thing as like what the atom does. It bends over and it releases something, but it releases a photon instead of a big sigh, right? And there's the units, or there's the equations that we talked about previously that are associated with that photon.
So energy is only done when they're emitting. I, is that,
Um,
so if it was like absorbing, it wouldn't, you couldn't solve for E.
you can still solve for E. So,
Okay.
yep. So it's just opposite, right? In order for the blue electron to go from n is equal to 1 to n is equal to 3, a photon has to come in with the correct energy to bump it up to that one, right? So if it only came in with 1,000 energy, it wouldn't bump it up. It would only bump it up to n is equal to 2. But if it came in with 2,000 energy, then it would. Does that make sense?
Yes.
Okay. And like that's where the photoelectric effect comes in. It's how can you excite this electron? How much energy do you need to put into the atom in order to excite the electron? Okay. So as an example, Yeah, I guess. Right, so we have a metal absorbs, or a metal must absorb radiation with a minimum energy of 3.97 times 10 to the negative 19 joules before an electron can be emitted. What is the wavelength and frequency associated with this electron, or with this energy? How can we solve this one? What do we need to use? Yep, we need to use our constants. What constants do we need to use here? Right, what, or do we know what equations we're using?
Can you do like E equals H? C over the wavelength?
Yep, right. So we need to know the wavelength and the frequency. So it doesn't really depend, it doesn't really matter which one we do first. If we solve for a wavelength first, then we can have the HC over lambda. Use it that way. We can solve for frequency first, and we can see that energy is equal to H frequency. And then we could use C is equal to lambda times frequency to solve for lambda, whatever one is easiest for you. But you do need to use two equations here to solve for both energy, or to solve for both wavelength and frequency. So if we were to solve for wavelength first, all right, we don't know wavelength. Oh, I'll just rearrange this. We rearrange the equation so that energy is underneath. We know our energy. So we can solve for this here. And we get 501 nanometers. Right, so again, that relates to the nanometer unit that we're looking for. And then we can either use that for lambda and frequency, and so we get frequency equal to 3.00 times 10 to the 8th meters over second divided by what we just found out. And this is pretty much 6.0 times 10 to the 14th hertz. And then if you wanted to solve or check either one of your answers, you could solve for then frequency first and see if you get the same frequency, and then if you get the same wavelength. Okay. Any questions on that? Does that kind of make sense how we use those equations? They're pretty straightforward as long as you know like what constants to use, what magnitude you're in and everything. And stuff like that. Any other questions we want to see today? I know we just took an exam, so probably rough on the brain. Okay, we can end there if there's no other questions. If you do have questions, feel free to come up and ask me. And I'll be in class on Friday as well. So if you have any questions, then feel free to find me.
Thank you.
Yeah, thank you. If you have any questions with homework or something, I'm happy to answer those as well.